Now let us understand this simple harmonic motion. For that, let us consider this figure. An object, let's say of mass m, is initially at point x is equals to 0. Now it is displaced from this position. It moves to point A, again comes to point x is equals to 0 and moves in the opposite direction up to point minus A. Here we are considering the surface to be smooth. That means there are no dissipating forces acting on this object. Now, at any point on the object, there will be a restoring force acting to take it to its initial position. This restoring force will always be in the opposite direction of the displacement. If the acceleration due to this restoring force follows the equation A is equals to minus omega square x, where A is the acceleration, x is the position at particular instant, and omega is the angular frequency of the material or object, then the motion is said to be simple harmonic motion. So, for any motion to be simple harmonic motion, its acceleration should follow the equation A is equals to minus omega square x. So, to prove any motion to be simple harmonic motion, there are 3 simple steps. First step, give small displacement from mean position. Here, small displacement is very important. Second, after giving the displacement, write all the restoring forces. From that, we can find the acceleration. Now, if motion is linear, then displacement will be linear. But if motion is circular, then displacement will be circular, the angular displacement. In that case, we have to write all the restoring torques. For example, in the case of pendulum, the displacement is angular displacement. So we have to give a small angular displacement theta, and then we have to write all the restoring forces or torques. Then we can find the acceleration from the equation A is equals to F by m, or alpha is equals to tau by I. Here tau is the torque and I is the moment of inertia. Alpha is the angular acceleration. After finding the acceleration, we have to compare it with the basic equation A is equals to minus omega square x in the case of linear motion, and alpha is equals to minus omega square theta in the case of angular or circular motion. If given acceleration follows this equation, then the motion will be SHM. And from this we can find the omega. Omega square is equals to A by x. Here we will not consider the sign minus because the negative sign indicates that the restoring acceleration is in the opposite direction of displacement. So, omega will be equal to A by x, and omega is given by 2 pi by time period, that will be equal to under root A by x. So, from this we can find the time period, that is equal to 2 pi under root x by A. So these are the simple steps from which we can check whether the given given motion is SHM or not, and if it is SHM, we can find the time period. First, we have to give the small displacement from mean position, then write all restoring forces in the case of linear motion and restoring torques in the case of angular or circular motion. Then find the acceleration E is equals to F by M, or angular acceleration alpha is equals to tau upon I. So acceleration will be compared with minus omega square x, or alpha is equals to minus omega square theta. From that we can find the value of omega, and from omega we can find the time period. Now let us prove that this sinusoidal function is SHM. This is the function of sine wave having amplitude A. So x of t can be written as A sine of omega t. This is the position time equation. The initial phase is 0 as the graph is starting from 0. Now, if we want to find whether the motion is SHM or not, we have to first find the acceleration. For that, we have to differentiate twice this position with respect to time. So v of t will be d by dt of x of t. So velocity will be equal to a, differentiation of sine omega t will be cos omega t into omega. Again, differentiate velocity with respect to time, we will get acceleration. A of t is equals to d by dt of v of t, that is equals to a omega. The differentiation of cos omega t is minus of sine omega t, and again differentiating omega t with respect to time, we'll get omega, that will be omega square. So a of t will be equal to minus sine omega t into omega square. But a sine omega t is the equation of position x, so we can write acceleration is equals to minus of omega square into x of t. Comparing this with basic equation, a is equals to minus omega square x, we can say that this follows the equation of SHM. So if the position time function is sinusoidal function, that is sine or cosine wave, then the equation will represent SHM. Now, what will happen if such functions are added together? Let us see. If two or more SHM are added, then let us see how we can check whether the resultant equation represents the SHM or not. For example, we are combining two equations, that is sine omega t plus cos omega t. Here both are individually SHM and they both are having same frequency, so the resultant will also be SHM. So let us note down, if all the functions added are SHM, and if they all have same frequency, then the resultant will also be SHM. as we have seen, the resultant will also have same frequency omega. So time period of resultant function is t is equals to 2 pi by omega. Now let us find the initial phase. Here the function sin omega t plus cos omega t can be written as sin omega t plus sine of pi by 2 minus omega t, because sine pi by 2 minus theta is cos theta. So this can be written as sine plus sine 2s is equals to s plus s is equals to 2sc. So it will be 2 sine of omega t plus pi by 2 minus omega t divided by 2 into cos of omega t minus pi by 2 plus omega t whole divided by 2. So this will give us 2 sine of this omega t will get cancelled out, pi by 4 into cos of omega t minus pi by 4. We know the value of sine pi by 4 is 1 by root 2. So 2 into 1 by root 2 is equals to cos of omega t minus pi by 4. So root 2 is equals to cos of omega t minus pi by 4. So the initial phase will be pi by 4. And root 2 will be the amplitude of the resultant wave. Let us see another example. The function is given x of t is equals to cos square omega t. You want to check whether it is SHM or not. If it is SHM, then we have to find the time period. Here, the cos square omega t can be written as 2 cos square omega t is 1 plus cos 2 omega t. So cos square omega t will be 1 plus cos 2 omega t whole divided by 2. So that will be half plus cos of 2 omega t by 2. This half cos 2 omega t is periodic function and it is SHM. But as it is added with a constant value half, it is not SHM. First thing to remember is we can never have the position equation as a square or cube or n power of the trigonometric function. The power must be always 1. So for that we have converted this using the trigonometric identity. So we got cos square omega t is equals to half plus cos 2 omega t by 2. This individual function is SHM, but as it is added with the constant value, it is not SHM. Let us see the next example in which x of t is given, let's say, cos cube omega t. Here again, first we have to convert it in power 1. The cos cube omega t can be written as 3 by 4 cos omega t minus 1 by 4 cos of 3 omega t. Here, these both are individually SHM, but their frequencies are not same. In the first case, frequency is omega, and in this case, frequency is 3 omega. They both are SHM, but as their frequencies are not same, the resultant will not be SHM. So it is not SHM as both have different frequencies. So in this way, we can find whether the given function is SHM or not. The equation of SHM can also be represented as a vector, which is called phasor. And we can also use the phasor method or the vector method to add the SHM. So let us see the phasor representation of SHM. Consider the general solution of SHM, that is x is equals to x naught plus a cos omega t plus phi. If we imagine a vector whose tail is at x naught, if we have considered initial position to be 0, then this x naught will be 0. But if it is not 0, then the vector will start at point x naught and its length should be equal to 1. It is rotating with an angular velocity omega. Then the coordinate of the shadow of tip of rotating vector is also given as x is equals to x naught cos omega t plus phi. So any SHM can be visualized as shadow of imaginary rotating vector. The particle will repeat its configuration after time 2 pi by omega, that is the time period of oscillation. The repetition of configuration means the repetition of position as well as the velocity. For example, two SHMs are given. x1 is equals to a1 sine omega t plus phi 1 and x2 is equals to a2 sine omega t plus phi 2. We can represent them as a vector. As initial point x naught is equals to 0, they will start from origin. The first vector will make an angle phi 1 with x-axis. So let's say this is vector 1 whose length or magnitude is a1 and it is making an angle phi 1 with x-axis. The second vector is a2 sine omega 2 plus phi 2. It will make angle phi 2 with x-axis. This is a2. So the phase difference between these two vectors will be phi 2 minus phi 1. We can find the resultant as a is equals to under root a1 square plus a2 square plus 2a1 a2 cos of angle between them will be phi 2 minus phi 1. This will be the resultant vector a, making an angle phi with the x-axis. That angle is given by tan phi is equals to a sin phi 1 plus a2 sin phi 2 divided by a1 cos phi 1 plus a2 cos phi 2. So in this way, we can write the resultant SHM whose amplitude will be this and whose angle can be written by this formula. Let us see some example based on the phasor addition of SHM. In this example, two SHM are given. x1 is equals to 2 sin omega t and x2 is equals to 3 cos omega t. We want to find the resultant of x1 plus x2. Here x2 can be written as 3 sine of omega t minus pi by 2 because that will be cos omega t. So the angle between this x1 and x2 is pi by 2. If we draw the phasor diagram, The initial phase of this one is 0, so it will be along x-axis only, and its length is 2. Now, the x2 is making an angle 90 degree with x1, and its magnitude is 3. This will be the resultant x. So, the magnitude of x will be equal to under root 2 square plus 3 square. That will be equal to 4 plus 9. So, x will be equal to root 13. The angle with x-axis will be tan phi is equals to 3 by 2. So x can be written as root 13 sine of omega t plus phi, where phi is tan inverse 3 by 2. So in this way we can represent the resultant wave. In the second example, there are 3 vectors or 3 SHM having all magnitude A. First one is A sine omega t, second one is A sine omega t plus 2 pi by 3, and third one is A sine omega t plus 4 pi by 3. Now let us first represent them in the coordinates. All 3 are starting from the origin. The first one has 0 initial phase, so it will be on x-axis only. So this is x1. The second has the phase 2 pi by 3. 2 pi by 3, that means 120 degree. So it is having magnitude A, it is also having magnitude A. This angle will be 2 pi by 3. And the third one is making an angle 4 pi by 3. 4 pi by 3 can be written as pi plus pi by 3. So this vector will be in third quadrant, making an angle pi by 3. And this total angle will be 4 pi by 3. They all are having same magnitude or same length as A. The resultant of this two, as the angle between them is 2 pi by 3, that is equals to 120 degree. The resultant will also have same magnitude, and it will be along the angle bisecting line. So as this is the 120 degree, the resultant will be at 60 degree. And it will also have same magnitude A. This A and this A are in opposite direction, so they'll cancel out each other. So the resultant of x1 plus x2 plus x3 will be equal to 0. In this way, we can use the vector method or the phasor method to find the combination of SHM. Now, let us see how simple harmonic motion and the uniform circular motion are related. Here we shall show that the projection of uniform circular motion on a diameter of the circle follows SHM. Let us perform a simple experiment. Tie a ball to the end of a string and make it move in a horizontal plane about a fixed point with constant angular speed. The ball is performing uniform circular motion. The ball appears to execute to and fro motion along the horizontal line with the point of projection as midpoint. You could observe the shadow of the ball on wall which is perpendicular to the plane of the circle. What we are observing is the motion of ball on a diameter of the circle normal to the direction of viewing. We can also consider it a ring. It is kept vertical and an insect is crawling over its rim. Now, due to sunlight, there will be a shadow of this ring with insect on the ground. Now, we can see only two-dimensional things on ground or surface like ground. So, we can see that as the insect starts from this point and it crawls up in upward direction, its shadow will move in this direction. Now when it has reached up to maximum height, its shadow will be at the center. Now again it is crawling down, so its shadow will be in this direction. Its shadow will move along this path. When it reaches this point, its shadow and the insect will be at same points. Now again it starts crawling in further downward direction, so its shadow will move again towards the center. At this point its shadow will be at center. Again it is moving towards its initial position and the shadow is moving along this radius. So for whole uniform circular motion of the insect, its shadow was moving along the diameter of the circle. So we can say that if particle is performing uniform circular motion on a circle, then its shadow or its projection on the diameter or its projection along the diameter will follow the simple harmonic motion. Let us define same situation mathematically. Let's say there is point P. Object is at point P at t is equals to 0. We are considering this to be x-axis. If it is starting at this point, then this angle phi will be its initial phase. Let's say it is reaching up to point P dash in time t. So, if it is moving with constant angular speed omega, then this angle will be omega t. The initial position vector OP makes an angle phi with positive direction of x-axis at t is equals to 0. And omega t angular displacement is made in time t. So we can say that at point P dash, the vector will make an angle omega t plus phi with positive x-axis. Now consider the projection of OP on x-axis. The projection of OP on x-axis is given by x of t is equals to, let's say radius of the circle is a, so that will be a cos of omega t plus phi. This is projection of OP on x-axis or along the diameter. And we have just found that whenever the equation of position is given by this sinusoidal equation, then that will follow the SHM. So we can write that the projection of particle performing uniform circular motion on its diameter follows SHM. So the particle is performing uniform circular motion, but its projection along diameter will perform SHM. Remember, the particle is not performing SHM. The particle's motion is not SHM because it is not oscillatory motion. Now, if at t is equals to 0, phi is equals to 0, then omega t plus phi will be equal to 0. So in that case, the particle will start from this point. Now at time t, when this particle is making an angle omega t plus phi with x-axis, this angle will be omega t plus phi. The projection on x-axis will be OP dash is equals to A cos of omega t plus phi. Now, when it is perpendicular, this angle will be 0. So in that case, we can write OP is equals to A cos of pi by 2, that will be equal to 0. So the object will be at its projection will have 0 length and it will be at the center of circle. Now as we move in the second quadrant, let's say at any time instant t, this angle will be omega t plus phi. So for omega t plus phi greater than 90 degree, its projection will have negative value. So in this way, for different kind of projections, we can find the amplitude of the SHM. The maximum amplitude will be the radius. So the particle P and the circle on which it moves are sometimes referred to as reference particle and the reference circle respectively. We can take projection of the motion of P on any diameter. So we can take it on y-axis also, we can take it on x-axis also. If we take it on y-axis, in that case, the displacement will be given by A sine of omega t plus phi. Let us see one example based on how we can represent the SHM on circular motion. In this example, we are asked to plot the corresponding reference circle for given SHM, that is x is equals to minus 3 sine of 2t plus pi by 4 in the anti-clockwise direction. First, let us draw the reference circle. here we can write x is equals to minus 3 sine of 2t plus pi by 4 as x is equals to 3 cos of pi by 2 plus 2t plus pi by 4, because cos of pi by 2 plus theta will be minus sine theta. So the angle would be pi by 2 plus pi by 4. So x will be 3 cos of 2t plus 3 pi by 4. So the angle with x-axis will be 3 pi by 4 and the radius of the circle will be 3 centimeter. So here the radius will be 3 centimeter. The angle is 3 pi by 4, that is pi by 2 plus pi by 4. It's in this angle, this point is O, this point is P. This angle is 3 pi by 4, this angle will be pi by 4. So at t is equals to 0, the particle will be at this point. If we can compare with the basic equation, x is equals to a sine or cos of omega t plus phi, then the omega will be 2, the SI unit will be radian per second, the initial phase will be 3 pi by 4 and the amplitude will be 3 meter. In this example, we have to obtain the SHMs of the projection of the radius vector rotating particle P in each case. So let us see each case one by one. In the first case, the time period is given 2 seconds. So let's say case 1, the time period is given 2 seconds. From this we can write omega is equals to 2 pi by t, that is equal to pi radian per second. Now at t is equals to 0, the particle is at point P making an angle 30 degree with positive x-axis. That means the initial phase of the particle will be 30 degree, that will be equal to pi by 6 radian. The radius of the circle is given a, so the amplitude will be a. So x of t is a sine of omega t plus phi, but we want the projection on x-axis, so we will use cos. So a cos of omega t plus phi. Here amplitude is a, cos of omega will be pi plus the initial phase is given pi by 6. So this will be the equation of the projection on x-axis for case 1. We can see that this represents the SHM. Now for the second case, here the time period is given 1 minute. So for case 2, time period is given 1 minute, that is equals to 60 seconds. So omega is equals to 2 pi by t, that is 2 pi by 60. So omega is equals to pi by 30 radian per second. Now, for the initial phase, here we can see that at t is equals to 0, particle is at point P, which is making an angle 90 degree with positive x-axis. So, the initial phase phi will be equal to 90 degree, that is equals to pi by 2. So, the position equation can be written as, or the projection on x-axis can be written as a cos of omega t plus phi. So, x of t will be, radius is a, cos of omega is pi by 30. So, pi by 30 t plus initial phase is pi by 2. So, this will be the equation in second case, and this will be the equation in first case. So, in this way, from the given circle, we can write the equations of SHM, and from the given SHM, we can represent it as a uniform circular motion. In this example, we want to obtain the equation of SHM of particle whose amplitude is 0.02 meter and whose frequency is 25 Hz and the initial phase is pi by 4. Here A is given 0.02 meter, the frequency is 25 Hz and initial phase is pi by 4. The position equation can be given as A sine of omega t plus phi. Omega is 2 pi by time period, but 1 upon time period is frequency. So omega is equals to 2 pi f. So omega will be 2 into 25, that will be equal to 50 pi radian per second. So put these values in this equation, we can get x of t is equals to amplitude 0.02 meter into sine of omega is 50 pi. So 50 pi t plus initial phase pi by 4. So this will be the equation of SHM for given data. In this example, the shortest distance traveled by particle executing SHM from mean position in 4 seconds is equal to 1 by root 2 times its amplitude. Find the time period. Here it is starting from mean position, so the initial phase will be 0. Let's say the equation is x is equals to a sine of omega t. It is given that at t is equals to 4, the x of t is a by root 2. So, we can write a by root 2 is equals to a sine of 4 omega. This a will get cancelled out, so we can write 1 by root 2 is equals to sine of 4 omega can be written as 2 pi by t. But 1 by root 2 is sine pi by 4. So we can write 8 pi by t is equals to pi by 4. This pi will get cancelled out. So we can write t is equals to 8 4 32 seconds. So this will be the time period. So in this way, from the equations of SHM, we can find different values. Now, for a particle executing SHM, let us find the time taken by it to move from x is equals to 0 to x is equals to a by 2. First, let us consider the situation. Let's say this is mean position, x is equals to a. This is one extreme position, x is equals to capital A. This is x is equals to 0. And the opposite extreme position, x is equals to minus a. if the particle starts from mean position, starting from this 0 to A, again at 0, minus A and 0, this total time is capital T. So from 0 to A and A to 0, this total time will be T by 2. So from 0 to A time will be T by 4. Either from 0 to A or from A to 0, time taken will be T by 4. Same way, in the opposite side, from 0 to minus A or from minus A to 0, the time taken will be T by 4. This is the midpoint A by 2. We want to find first the time taken from x is equals to 0 to reach x is equals to A by 2. Here, as it is starting from mean position, the initial phase will be 0. So we can write the equation x is equals to A simply sine of omega t, because phi is 0. We want to find the time t, where the position is A by 2. So we can write A by 2 is equals to A sine of omega t. This A will get cancelled out. So we can write half is equals to sine of omega t. But half is the value of sine 30 degree. So sine pi by 6 is equals to sine of omega t. So pi by 6 is equals to omega t, and omega can be written as 2 pi by capital T into t. So pi by 6 is equals to 2 pi by capital T into t. This pi will get cancelled out. So small t will be equal to t by 12. This is very important result. Time taken by particle to move from 0 to A by 2 or from A by 2 to 0 will be T by 12. This time will be T by 12. Now we want to find the time taken by the particle to move from x is equals to A by 2 to x is equals to A. Now let's see. From 0 to A, total time is T by 4. From 0 to A by 2, total time is T by 12. So, from A by 2 to A, the time will be T by 4 minus T by 12. So, this will be 3T minus T divided by 12. That will be 2T by 12, that is equals to T by 6. So the time taken by particle performing SHM to move from A by 2 to A or from A to A by 2 will be T by 6. In the same way, we can write on the opposite side. If this point is minus A by 2, then this time gap will be equal to T by 6, and this time gap will be equal to T by 12. Here we can see that the time taken by particle to move first half of amplitude, that is first A by 2 distance, is T by 12, and next same distance A by 2 is T by 6. So time taken in first case is lesser than the second case. This is due to the decreasing velocity that we will see while we learn about the velocity position equation and the acceleration position equation. So for now, keep this in mind that from x is equals to 0 to x is equals to A by 2, time is T by 12. From A by 2 to A, time is T by 6. And from 0 to A, one time journey, the time is T by 4.